Okay, so let's take a look at using our time value of money thinking to answer some interest rate questions. So let's suppose I get 3% every quarter. How much will I earn every year? So if I go to financial calculator here, so we're getting 3% every quarter, so we'll put that in there, 3%. Now it says every quarter, and so our time word is going to be months. So I'm going to put in 3 here. It's a quarterly rate compounded every quarter, so 3 months, 3 months. And the question was to convert that rate to an annual rate. So 12/12 is 12-month, a 12-month rate compounded every 12 months. Now just to show you, right, if I leave this 3, this changes it to 12% by multiplying by 4. And so we can do straight multiplication to change rates, but only to change the time frame, not the compounding frequency. If the compounding frequency changes, that won't work. So we go back to 3%, and this time change the compounding frequency. We get a different rate. It's not 12% anymore because we're compounding less frequently, and so we need to have a higher rate to get to the same place. So that's why it's bigger than 12%, is because we're compounding less frequently, so we need a bigger rate. Another example would be an annual rate compounded semi-annually to an annual rate compounded annually. Now this is significant in finance because corporate bonds, debt securities issued by governments and large corporations, typically pay interest payments every 6 months. So the natural compounding frequency for these type of financial securities is 6 months, but we might be interested in what our actual effective return would be over the course of a year. So using the same method, we can say, okay, here's our 6%, and we need to know what units do we have. And the units we have, it said it was an annual rate compounded semi-annually. Oops, that Y won't help us. Annual rate compounded semi-annually, and we want an annual rate compounded annually. And it ends up being a little bit bigger than 6%. Again, because we're compounding less frequently, so we need to have a larger interest rate to get to the same place. So if you get 10% every 6 months compounded monthly, what is that rate as an annual rate compounded annually? So go ahead and try it. I have the answer there for you. You should get 21.94%. But pause the video and see if you can't get that answer using the financial calculator. Okay, let's see how we did. So we have 10% every 6 months compounded monthly. So 10% is here, 10%. So it was every 6 months compounded monthly. And so 6 months compounded every 1 month. And we want that as an annual rate compounded annually. So once again, 12/12, and we get 21.939 actually, but by the time you round, it gets to 2.2194. Hey, I have some completed example in the slides on how to do this, and some questions that you can practice here. But the best way to do it is in the time value of money practice in the week 2 folder. There are some questions on Blackboard. Obviously, your homework isn't Connect, so these are not homework questions. They're not graded, but you're welcome to use them for practice. I've posted the solution to these problems as well if you get stuck. But now would be a great time to pause the video and give it a shot and see if you can answer the first 5 questions in the time value of money practice. And if you, it should give you feedback right away. You just submit it, you're allowed to take it as many times as you want. So it should let you know right away if you're sort of getting it, and if you can do these 5 questions, then you should be in good shape to deal with interest rates on the homework. So go ahead and give it a shot, and we come back. Well, pause the video and then come back, and we'll work on the next concept. Okay, hopefully that went well. So now we are going to start thinking about introducing the time value of money. So to introduce this concept, we're going to start with a metaphor of a checking account and being at a bank. So suppose you're standing in the lobby of a bank, and a close friend walks up to you, and the key in all of these examples is that this friend is trustworthy and reliable, and will obey the law. So if he contractually obligates himself to pay you some money, this will happen with certainty. Now, obviously, in real life, this is not the case. He could be arrested and imprisoned and then be unable to pay you, and maybe he gets sick, or there's lots of things that happen, but we're going to abstract away from all of that and just assume that he's a perfectly responsible person who can make good in everything he says. And so this person approaches you in the bank and offers to transfer to you a savings account with a $100 balance in it. So that's nice, right? That's a pleasant thing to do. But the key here is that this person is willing to transfer the savings account to you for a price. Traditionally, at this point, we would decide collectively as a class what name we want to give our close friend. In my head, I call them the Bob problems because the first time I taught this lecture, Bob was the name everyone chose. So we'll stick with Bob in this class, since I can't ask you on the fly anyway. So Bob has a $100 savings account, and he wants to know what you'll pay him for it. And the question first is, what's the most you would pay for the savings account? I think it's pretty clear that you wouldn't pay more than $100, right? If you pay $101 for a $100 savings account, that's just wasting $1, right? It's silly. You won't get any. You'll be working backwards. Now, what if it was less? What if it was $99? Well, then you have an obvious thing to do. You pay Bob $99. Bob gives you access to the savings account. You walk to the teller 10 feet away, and you say, I would like to remove $100 from my savings account. And now you're up by $1. And so really, any price under 100 doesn't make sense, because it would be instant profit. And $1 of instant profit you'd happily take, but you probably actually happily take 50 cents of instant profit, or even 25 cents of instant profit. I mean, at some point, walking the 10 feet to the teller isn't worth it, but really those are the kind of concerns we're not really worrying about in this case. And so because that $100 checking account is instantly convertible to $100 in cash, the only price for that account that makes sense is $100. And that's important, because for us, it feels $100 in a checking account or a savings account feels the same thing as $100 in cash, but they're not the same. Cash is liquid actual currency, whereas a $100 account is a claim on currency. It's a financial security. It's a very simple claim. The claim is show up anytime and get your money. But not all claims are that simple. And so we're transitioning from a cash world where we have a $100 bill into a financial claims world where we have a claim on a financial asset, in this case, $100 of cash and deposited at a bank. Now for bank deposits, the cash and the deposit feel very similar. In fact, we use them almost exactly the same way. If I walk into Walmart, I can pay using my bank deposits, or I can pay using cash, and they don't care. But as we work forward, we will start putting some stipulations or increasing the complexity of the financial security, but ultimately they will still be claiming cash, but possibly with some additional restrictions. But this is the simplest case. We start with a $100 savings account. The price must be $100. Situation 2. So suppose the bank that we're in the lobby of has a CD they're offering that stands for certificate of deposit. It's a contract with the bank where you give them money and you're not allowed to remove it without penalty over the course of the time period. But if you leave it for the length of time specified in the CD contract, then you're given an interest rate promised on the contract. So in this case, the bank says if you deposit $98 with them on a CD, they will give you $100 a year later. Okay, so that exists in the marketplace. So enter Bob, and he says, have I got the deal for you? I've got a savings account, but I fell and broke my arm on some steps at my apartment, and I got a settlement from my landlord, and even though I don't have any money in this account now, in 12 months' time, I'm going to get a $100 payment in that account as part of my structured settlement. So there's nothing in there now, but in a year there will be $100. And so I want to give you this savings account, and I'm wondering what you'll pay me for it. Okay, so right in the old situation, we would give Bob $100 because we could immediately convert that $100 to cash. But that is not so in this case, right? There is $100 available to us in that checking account, but not immediately. And obviously, $100 1 year from now is inferior to $100 right now, or we don't like it as much. So, reasonably, $100 is too high a price to pay for that. So, what is the appropriate price for this security? Well, if you think about it, right, what if we pay Bob $99? What does that mean? So we would pay Bob $99, and then a year later, we would get $100 from Bob. And so we get paid a $1 payment for patiently waiting to receive our money. And that might be enough for us emotionally, but it doesn't make sense to do that rationally, because I could pay the bank $98 instead of $99, have $1 left over for a chocolate chip cookie at McDonald's, and end up in the same place. Right? So because the market is offering a $98 to $100 conversion, paying $99 to Bob doesn't make sense. Similarly, if we offer Bob $97, we get in a kind of a similar problem, but it's a little different character. So if we offer Bob $97, he says, sure, I'll take it. And then we do something interesting. So the next person who comes into the bank looking to buy a CD, we say, hey, tell you what, I will give you, if you give me $97.50, I will give you $100 in 1 year's time. So that's 50 cents cheaper than the bank. So I can beat the bank. So go ahead and let's do this. And then you turn around and take 97 of that $97.50 and give it to Bob and buy his checking account. And now in Bob's case, he maybe only has one of these, but in the financial markets case, there's usually a very large supply of these kind of securities. And so you could buy from Bob for $97 and sell to the customer for $97.50 and pocket the 50 cents. And you would do it over and over and over again. And so what would happen is eventually you would exhaust the supply of people willing to give you money for $97.50. Maybe they would only be willing to do it for $97.25. And potentially you will exhaust the supply of Bob funds. And so eventually you get to $97 moving up to $97.25, and 97.50 moving down to 97.25, and then it matches when we're in equilibrium and profits can no longer be made. And so this is a key to understanding the price at which money travels through time, as it's dictated by the market, which is itself dictated by the aggregate impatience of the participants. Right? If everyone was way too impatient to put up with getting $2 to wait a year, then the bank wouldn't be able to offer that kind of CD rate because no one would take it. No one would deposit at that rate. Then they wouldn't have deposits with which to lend. So the rates that exist in the marketplace are to a great degree a function of the aggregate impatience of the participants in that market. Even the Federal Reserve, which basically sets the short-term interest rate, Ben Bernanke, after he'd left his post, had a nice comment about how basically their job at the Federal Reserve is to set interest rates to be consistent with what the market will bear. They have some wiggle room in maybe pushing things lower or higher a little bit to serve a monetary economics purpose, but really they're limited in how much they can push the interest rate outside of its natural location. And so the Fed gets criticized for keeping interest rates low for so long, and his argument was that interest rates are naturally low and there's only so much the Fed can do to move them outside where they naturally belong. And so really when we talk about an interest rate, which is just a payment for being willing to delay, the longer the time, the more the payment, and those payments are dictated by the market. So let's keep it going. So we'll go to situation 3. So suppose a friend offers you $100 in 2 years. What would that be worth in 1 year? And so let's think about this position 12 months from now. So if you're 12 months from now, what does this look like? Well, 12 months from now, you're getting $100 12 months from now. So do we have a price for $100 12 months from now? And we do, right? That price today is $98. Now here's the trick. We don't know for sure that $98 will be the price a year from now, but the current price for $100 a year from now is probably the best guess for what the price will be in a year, right? So in 12 months, the most likely scenario in our mind is that 98 will turn to 100, but we don't know. So if we have $100 in 2 years, in 1 year, that our best guess is that it will be worth 98. So the answer to situation 3 is actually the same as the answer to situation 2, except for in this case, we're looking at the difference between money arriving in year 1 and money arriving in year 2, instead of money arriving in year 0 today and money arriving in year 1. And that's important because this is how we're going to extrapolate into longer time horizons, which we'll do in situation 4. So suppose the same friend offers you $100 in 2 years. What would that be worth in today? There we go. Sorry. So yes, so situation. This is situation 4. Situation 4 and 3 where it was a typo. It's the same thing. So 5 is the new 4, I guess. So what would it be worth today if we were getting $100 in 2 years? Okay. So let's think about how we would answer this. So let's get to Excel, and we'll do this in parts here. So let's make a timeline here. So we have 0, 1, and 2, and we know that we have 100 here. Okay? And another way to think about this is if I have 100, if I have $1, right, what happens to that dollar? That dollar turns to 98 cents if we go back one, right? because that was the deal that we got from the bank. Every dollar is, if you pay 98 cents, you get a dollar later. In their case, it was 100 times bigger than that, but we get, right, that's the general principle. And so if we think about 100 here in year 2, that should translate to, right, we have 100 of these, right, we have 100 $1 payments, and so they should cost 98 cents each, right? We have 100 of them, 98 cents each, $98. So this is that, you know, scenario we're familiar with, where 98 turns to 100. But what about here? What about here? So we decided our best guess was the same price, that we would still have 98 turning to 100, but now I only have 98 of them. So I'm going to take 98 and I'm going to multiply by 98 cents, because I have 98 $1 securities that each cost me 98 cents today to buy. And I get 96.04. Okay, notice it's not 96 even. Why is that? Because if we had 96 even, it wouldn't turn to 98, because 98 turns to 100. Right? We have to have a little bit more than 96.04 to get there. Okay, so this is just using the same logic twice. Right? 100 turns to 98, and then 98 turns to 96.04, because each dollar costs 98 cents. Okay, so that's situation 5. So what we've done here is we've moved money through 2 years in time now, right? And if you think about that process, we could do this over and over and over again, and we can move money as many times forward and backwards as we want. Right? So that's where we're going to get to in situation 6. Now I'm changing the interest rate a little bit in situation 6 to make things simpler, because if you go back and look at this, what is the interest rate here? Well, the way we calculate interest rates would be to actually take the return later divided by the return now minus 1. You see, this is not a 2% interest rate. That's a 2.04% rate, which is a little inconvenient to work with. So we're going to change the bank's offer going forward. So the new offer is you put $100 in, and the bank gives you $102 a year later, which is a nice even 2% interest rate. Right? If I go in Excel, I do 102 divided by 100, you get, minus 1, you get an even 2%. Right, even 2%. Okay, so we'll do that. So we're back to Bob. So suppose Bob offers you $102 in 2 years and $2 in 1 year. What would it be worth today? So let's make a map of that. So we have the same time periods here, but we have 102 here and 2 here and question mark, right? Question mark. So I'm going to do this in steps. So let's follow the same logic. So this 102 here, what is that worth? Well, we know that 102 in 1 year in the future is worth 100 in the present. So this 102 is going to turn to 100 in year 1, right? So 100 in year 1 deposited at the bank produces 102 in year 2. And actually we're going to do now a subtotal, right? Because I have effectively $100 in year 1 money and $2 in year 1 money. And if I give you, think about this, if I give you $10 in a month and I give you $20 in a month, it's perfectly reasonable to say I'm getting $30 in a month, right? The 10 I receive in a month and the 20 I receive in a month, I can put together and get 30 in a month, and that's fine. If I were to say I'll give you $10 in 1 month and $20 in a year, it would not make sense to put those together, right? Because you could take the $10, put it in the bank, have it grow to $10.10, and now you have $30.10, right? The fact that they show up in different times means you can't add them because they're not truly the same number. They have different units. But these are in the same time, right? They're both year 1 values. So if we add them, we get 102. Oops, 102. Okay, so if I have 102 in year 1, what's that in year 0? Well, we know what 102 in year 1 turns to. It turns to 100. So this whole security here, this whole security is actually worth $100. Another way to think about it is we can replicate these payments by depositing $100 at the bank. Right, 100 would turn to 102. We pull 2 out. We're left with 100. That 100 turns to 102. We pull 102 out. We're left with 0. And there's our cash flows we're looking for. Right, so this is our bank balance before and after. And this is the cash removed over the course of our transaction. So we can replicate the cash flows of this using a $100 bank deposit. So this is an important concept in financial valuation, is we can replicate, if we replicate the cash flows perfectly, then whatever it cost us to replicate them is the price of the thing. So because we can make a 102 using a $100 deposit, it must be that this security costs $100. Okay, so let's take a look at the next one here. So suppose the same friend offers you 102 in 5 years and 2 in year 1 through 4. What would that be worth? Okay, right, so new scenario, 2, 2, 2, 2, 102. Right? Years 1, 2, 3, 4, 5. If we think about this, right, 102 is going to turn to what? 100. Total it up, 102. That 102 is going to turn to 100. Total it up, 102. 102 is going to turn to 100. Total it up, 102, and so on, right? Total it up, 100. So 102 is also 100 by the same logic. So we're getting to a general principle here where we can move money through time and aggregate up multiple payments once we have everything in the same time frame. And these are going to be key skills to working with time value of money. Okay, so I'll take a break real quick, and then we come back, we'll pick up with some additional situations to think about.